Hello everyone, this is another problem of the week solution video, this time for the problem alphabet spam. As usual, we'll read through the problem and then review an example solution in Python. Here is the problem description. About 90% of the 300 billion emails sent every day are spam. Thus, a fast spam detection mechanism is crucial for large email providers. Lots of spammers try to circumvent spam detection by rewriting words like money, cash, or lottery, but that substitutes the letters for some numbers, so it throws off the spam detection. A very simple and fast spam detection mechanism is based on the ratio between whitespace characters, lowercase characters, uppercase characters, and symbols. Symbols are defined as characters that do not fall in the first three groups, so examples of those would be punctuation or stuff like numbers. It says here that an input consists of one line with a string consisting of at least one and at most 100,000 characters. It also says that a pre-processing step has already transformed all whitespace characters to underscores, and the line will consist solely of characters with ASCII codes between 33 and 126 inclusive. This will come in very handy later, because instead of matching letters to each other, we'll just have to compare their ASCII value, which is just a number, to a range of acceptable values. It says here that our output will be expecting 4 lines containing the ratios of whitespace characters, lowercase characters, uppercase characters, and symbols in that order. And it also says that our answer has to have an absolute or relative error of at most 10 to the power of -6. So this basically says that you have to get the value to the nearest 1/millionth. So this won't be an issue in Python. However, in other languages where you're able to choose between 32-bit and 64-bit wide floating point numbers, you might want to consider the double width version or 64-bit version. In my Java solution, I elected to use the double instead of the float type because the float type was not precise enough. And here it gives our sample inputs and outputs. As we can see here, there are 4 ratios that we give right here. So with our understanding of this problem, it seems essentially necessary to use ASCII values. Firstly, you might ask, what even is ASCII? Well, all we need to know for this problem is that it's a character encoding standard that tells you what numbers go with what letters, basically turning letters into binary that a computer can understand. Let's head over to this ASCII table so we can get more of an idea of what's happening. Alright, so in the problem description, the first thing that they mentioned was that our inputs would consist only of characters ASCII codes between 33 and 126. So let's go to 33. 33 is right here, starting with exclamation mark. Notice how it excludes number 32, which is a space. So additionally, if you recall, they also told us that they filtered whitespace characters. They were all converted to underscores. So that is an important thing to note. And so we only have underscores, lowercase characters, uppercase characters, and symbols. Looking through this table, it seems that underscore is number 95. So there we have underscores, and let's look for lowercase letters now. So lowercase letters are between 97 and 122. Next is our uppercase characters, which seem to be between 65 and 90. And symbols are just everything else. So ignoring 95, 65 through 90, and 97 between 97 and 122, we know that everything else is just symbols. So knowing this, let's head over to our code. Alright, so the first thing that we do here is make these 5 variables. We have our space, we have our lowercase, uppercase, and symbol counters, which are basically there to keep track of how many we encounter in each of these inputs. Then we just get our input and save it to this variable. Since we don't need to work with it in any other format than a string, it's not casted to anything. In Python, you can work with strings in a similar way that you do with a list. Doing a for loop in something would just make it so that you iterate through each letter. So we have this for loop and we have all of our processing in here. So the next thing we have to do is get the ASCII value of that letter. It's pretty easy in Python. We just do that using the ORD method, which returns an integer, which is saved to this num variable. This if and else stack right here is pretty much responsible for determining which type of letter each of these letters are. As mentioned before, underscore is ASCII code 95, lowercase letters are between 97 and 122, uppercase letters are between 65 and 90, and symbols are just everything else. So we basically implement this using this stack. So if the code is 95, we'll increment the white space counter by 1, and then so on for each of the other ranges. Last thing we do is we'll just print out everything that we need out of these 4 variables. To do this, we use a tuple in line 19 that is constructed with all of these 4 variables in them. A tuple is kind of like a list in Python. However, the biggest thing that it's probably different compared to lists is that it is immutable. You can find lots of information online about it, such as within the Python docs for any recent version of Python. The most important part is that it's still iterable, which makes it very easy, since we can just make a for loop and just iterate through all of it. Since we're aiming for the ratio of each of the letters, we just print out the count divided by the total length of our input stream. And that is pretty much it for the code. We'll just print out all of these ratios, all 4 of them, and that should be our program. And let's try out some of our sample solutions. I'll just copy them from the website because the inputs and outputs are not very readable. So here's our for our first input stream. And here are our numbers, and let's just kind of remember what they look like. They look pretty much the same, so let's just call it good, because remember, we're just aiming between the nearest millions, so I think that's 10 to the power negative 6. And our next sample input, this gibberish. And that looks pretty much the same. Alright, that's all I have for this solution video today. We'll see you everyone.